Okay, hi. So we'd like to construct a circuit that's going to be able to add binary numbers, right? So what we're really trying to build here is some kind of logic component to add binary numbers. Okay, so to consider this a little bit, well, let's think about the binary addition rules. Okay, so we can say rules of binary addition. So these rules are pretty straightforward, and there's a video up on YouTube just explaining binary addition a little bit further with some examples. But the rules are straightforward. So we have 0 plus 0. Well, this is going to be equal to 0. Now 1 plus 0 is equal to a 1. 0 plus 1 is equal to a 1. And 1 plus 1 is equal to a 0 carry a 1. Okay, so now let's just consider this. Okay, so if we were to look at these different rules, or I guess the rules of binary addition, well, we can see that we have this idea of whatever the result is, right? So the result is a sum. Then we have the idea of some kind of carry, okay? So essentially what we're going to have here is we have in our inputs here, we're going to have a bunch of inputs. And so the circuit is going to actually look like this, right? So we're going to have inputs going in to some component. And then the output of the component, well, we're going to have an output for sum. And we're going to have an output for carry. So if we look back at our addition rules, well, we can say that 0 plus 0 is equal to 0, carry 0. 1 plus 0 is equal to 1, carry 0. 0 plus 1 is equal to 1, carry 0. Okay, so the idea is that we have this implementation where we're definitely going to get out the sum, so the actual addition of it, and sometimes the addition has this additional carry component associated with it. Okay, so let's look at a circuit that is able to do this. Yeah, so one of those circuits that's able to take two binary digits and produce this kind of output is known as a half adder. Okay, so we can say the component that we want to consider is called a half adder. And what this does is it takes in two binary digits and produces a sum and a carry. Okay, and let's look at this particular gate. Okay, so we're going to I suppose we're going to use or represent the binary digits as A and B. These are our inputs. And how this actually works is we're going to take an A, we're going to take a B, we're going to pass it in to an exclusive OR, and this is going to produce the sum Okay, and now let's consider that. So if we think about the exclusive OR piece, okay, so we think about the actual gate itself. So if we look at the truth table for exclusive OR, we have A is true, true, false, false. B is going to be true, false, true, and false. Then you have A exclusive OR B. Well, the exclusive OR gate says that if we have an odd number of trues, well, then the output is going to be a true. If we have an even number of trues, the output is going to be a 0. So if we say true and true, here is going to be a false. true and false is going to be a true, false and true is going to be a true, and false is going to be a 0. Sorry, it's going to be a false. Okay, so this looks cool, yeah? Because what we're seeing here is, well, if we consider this particular thing here, and if we were to change these trues to being a 1 plus a 1, well then the XOR gate is going to give me a 0, right? A 1 plus a 0, it's going to give me a 1. A 0 plus a 1 is going to give me a 1, and a 0 plus a 0, it's going to give me a false. Okay, so this is excellent, yeah? This shows that the XOR gate is able to actually give me the sum piece or the sum output associated with my addition of two binary digits. So the only other thing is I need to be able to work on the carry, okay? So, well, let's consider the carry, right? So in all of these examples here, well, the carry is a 0, right? So if we were to look at all of these outputs here, okay? So, and let's consider them first of all in terms of 1s or 0s, and then in terms of trues or falses. So if we have a 0 plus a 0, this gives me a 0, and it's going to be a carry of a 0, which is a false. A 0 plus 1 gives me a 1 with a carry of a 0, which is also a false. A 1 plus a 0 gives me a 1 with a carry of a 0, which is a false. And then a 1 plus a 1, well, this should give me a 0, so in the sum, and it gives me a carry of a 1, which is true. So now if we consider the output true, false, false, and false, well, this is the same output as what we would know from our AND gate, isn't it? So if we have A and B, we have true, true, false, false, true, false, true, or false, and then A and B. So AND means that both of them have to be true at any particular time to yield a true. So true and true is true, true and false is false, false and true is false, and false is false. So if we think about this and if we look at our AND gate, well, the AND gate actually gives us exactly what we want, yeah, or what we need from the carry of the binary addition. Right, so we can say that this is perfect, yeah. Oh, let me grab the blue. We say this is perfect for the carry. Okay, so let's join this in. So all we need to do now is we need to take a signal from A. Right, we bring it down. We're going to pass this into an AND gate. And this produces the carry. Okay, so now we have completed our half adder. So the half adder is quite a simple circuit. So we use the XOR piece or the XOR gate to produce the sum, and then we use the AND gate to produce the associated carry with doing simple binary addition. Okay, let's go back through this a little bit, yeah? Okay, so the idea was that we wanted to be able to start off to produce a logic component to add two binary numbers, okay? And really this is two binary digits, yeah? Okay, so two binary digits. So now we needed to consider, well, the binary addition, right? And really when we're considering the binary addition here, what we needed to do was to look at, well, what is the output of these, okay? So we look at the output of the XOR gate and then the output of the simple AND gate. Okay, and when we look at both of these, well, we're able to then look and see, well, this is going to be, we needed at least two outputs. So one output was going to be the sum and the other output had to be the carry. So in binary addition, if we have 0 plus 0, we get 0 with a carry of 0. 1 plus 0 gives us a 1 with a carry of a 0. So we just need to note the carry as well. So now we bring this down and we say, okay, well, the actual circuit that we're trying to build is known as a half adder. And the half adder takes in two binary digits and produces a sum and a carry. And the idea is that you would add loads of these different things together to be able to do full calculations. So we take our two input signals, our two binary digits, right? So just very important to note that these are our binary. Oh, the binary digits, yeah. Right, are our signals. And when we take those binary digits in, well, the XOR gives us the sum, and then the AND gate gives us our carry. So just to further explore this here, what we did was we actually looked at the truth tables, right? And then we mapped the truth tables so to the actual binary addition and what we're looking for. And then when we look at our particular rules, well, we should be getting all of the outputs associated with the sum and the carry. So let's take a little look, okay? So I'm going to draw just a very simple truth table that's going to show the function of this, okay? So really we need to have A and we have B, and A is true, true, false, false, true, false, true, and false. And what we said was we need to have A exclusive or B, and then we need to have A and B. Right, so now we have true exclusive or true is going to be false, and then A and true and true is true. We have true exclusive or false is going to be true. True and false is false. False exclusive or true gives a true. False and true gives us a false. And false exclusive or false gives us a false. And the false and false gives us a false. So if I was to just write down this in numerical format, yeah, so if I say A, B, and we have, it's going to be 1, 1, 0, 0, 1, 0, 1, 0, and exclusive OR, and A and B. So 1 exclusive OR 1 gives me a 0, 1 and 1 gives me a 1. So how we can read this is, I can say, if I was to say 1 and 1 is going to yield a 0 with a carry of a 1. So again, the exclusive OR represents the sum and the AND gate represents the carry. So now we have 1 exclusive OR 0 gives us a 1, 1 and 0 gives us a 0, and again 1 and a 0, and a 0 and a 0. So we can look at the sum and the carry, yeah? So we have 1 plus a 1 gives us a sum of 0 with a carry of a 1, and so on down. So we can read down through this truth table, simply here saying is 1 plus 1 is 0, carry a 1, 1 plus a 0 is 1, carry a 0, and so on and so on. So we can see the construction of this particular gate here is quite simple. We analyze the rules of Boolean addition. We denote that we need to have something to represent the sum, something to represent the carry, and then the gates that we need is the exclusive OR and the AND gate. Okay, well, I hope this makes sense. And if it does make sense, well, all that's left to do is to just simply draw a little happy face. Okay, thank you.